So now we're going to talk about some special series, Taylor and Maclaurin series. And so, we have been discussing quite a bit of infinite series. And we recently finished talking about power series. So a power series is a specific type of infinite series. And considering our power series, we had two basic forms. We had one form where it was centered at 0, and then another form where it was shifted and centered at some a value. Okay, so it was simpler and easier to deal with when it was centered at a. So we're going to talk about two specific types of power series. The first one is the Taylor series. Okay, so the Taylor series is a powerful type of power series, but the Taylor series can be a little bit more difficult to work with. So we have a simplified version of the Taylor series, which we'll call the Maclaurin series. Okay, so we've learned about all of these different types of series, and I just think it's helpful for us to see that they're all, related. And the Maclaurin is a subset of the Taylor, which is a subset of the power, which is a subset of our many types of infinite series. So, as I just said, the Taylor series is more powerful, but it's a little bit more difficult to work with. So sometimes we deal with a Maclaurin series, which is a specific type of Taylor series. It's not as powerful, but it's easier to deal with. It's a simpler Taylor series. So what we have here is our definition of a Taylor series, and then more simply, a Maclaurin series. So a Taylor series is generated by, we have this function with infinite derivatives, right? So thinking about a polynomial, you can take, if it was a 9th degree polynomial, you'd have to take the derivative 10 times before you got to a constant. And you can still take the derivative of that constant, right? So it's infinitely differentiable, a lot of these polynomials, which was something that was important about our power series. But we have a function with derivatives of all orders throughout some interval containing this a value at some interior point. So the Taylor series is generated by summing all of these derivatives. So the first one being the function, and the next term has the first derivative, and that function is essentially divided by 0 factorial. The first derivative is divided by 1 factorial. So then we have, you notice, the second derivative divided by 2 factorial. So the 0 factorial and the 1 factorial, those aren't written in the problem here or the definition because they're equal to 1. But I want you to see that this pattern that we're looking at is really what is resemblant of the Taylor series. So if this was the fourth derivative, I would have 4th factorial here. And then this x minus a value is would be to the 4th power, right? If this was a 4th derivative. Of course, it's not. That's the second derivative. So here's my nth term. Okay, so some derivative evaluated at that point A divided by a factorial of the same value of which the derivative we've taken, and then x minus a raised to that nth power. And the only thing that's different for our Maclaurin series is that it's at x equals 0. So instead of having all of these x minus a's, x minus 0 is just x. So when you go and notice here, we don't have x minus a to the k, we just have x to the k. X to the 0th is 1, so we don't have that written there. X to the first, x squared, all the way up to x to the n. Okay, so we'll really focus on Taylor series and just note that Maclaurin is a more basic version of the Taylor series because it doesn't have this extra a value in there. We're using 0 instead. So here we're going to go through the process to determine the Taylor series, which is generated by this function, f of x equals 1 over x. And we're going to do so at some point a equals 2. So the only difference if this was a Maclaurin series is that a value would be equal to 0. But here we have a equal to 2, so we're dealing with a more general Taylor series. And so after we've done that, we're going to say, well, where, if anywhere, does the series converge to 1 over x? So the first thing we're going to do here is we're going to find our function values and our derivatives evaluated at 2. So we are going to need to know what f of 2 is, what f prime of 2 is, what f double prime of 2, and, depending on how far you were going in the problem, you might need to find the third derivative, but the second should be suitable for our needs here. So we're going to evaluate the function, the first derivative, and the second derivative at some a value equal to 2. So one thing we know, I can find f prime, and so thinking about the fact that f of x is x to the negative 1, f prime of x would then be negative x to the negative 2. And f double prime of x, taking that derivative again, I'm going to get positive 2 to the x minus 3. So let's just look at what my nth derivative might be. And we might need to continue a little further. So my third derivative of x would be negative 6x to the negative 4th. My fourth derivative of x would be positive 24x to the negative 5. And so what you notice here, positive, negative, positive, negative, positive, it's definitely alternating. So f, my nth derivative of x, I know I'm going to have a negative 1 to the nth power. And if we look at these coefficients, our coefficient is 1, 1, this 2 is 2 factorial, 6 is 3 factorial, and 24 is 4 factorial. So we could then write this, well, this would be n factorial, and we have an x to some negative power, and that negative power is increasing, so I'll say n plus 1. So I cleaned that up a little bit. The point being, we can determine a general nth derivative. Okay, so I found my derivatives. I need to evaluate them all at my a value, which is 2. So f of 2 is positive 1/2. F prime of 2, I get negative 1/4. And f double prime of 2, I get positive 1/4. So how would I write my Taylor series, right? So that's what we're going to write out now. And so what this Taylor series would look like, according to our definition, is going to be f of 2 plus f prime of 2 times x minus that a value 2 to the first power, which we don't have to write to the first, minus f double prime of 2 over 2 factorial, and that would be times x minus 2 squared. Continuing along to some nth, we would have f to the nth derivative of 2, x minus 2 to the n over n factorial. And of course, these first two terms, that's over 1 factorial and over 0 factorial, but 1 factorial and 0 factorial are both 0. And if we take our specified function and derivative values, right, these guys right here, and we plug them in, we can simplify this just a little bit here. So I end up with 1/2 minus 1/4 x minus 2 plus 1/8 x minus 2 squared minus something, continuing along. I don't need to write minus plus, but continuing along, we're going to have -1 to the n, x minus 2 to the n, over 2 to the n plus 1. So now I've written out my Taylor series polynomial. And if we start to examine this, we can determine that it's a geometric series. And we know it's geometric, again, because we can always take a term and divide it by its preceding term. And that's going to give us a constant ratio. And it should for any two terms. So this next division here, if I take that and divide, it's going to give me the same value. And so what that we get, or what we end up with here, is we have our first term is 1/2. And my common ratio, if I calculated that, my common ratio would be negative x minus 2 divided by 2. Okay, so we have generated our power series. We know that it's geometric. We've identified the first term and my ratio. And we want to say, well, where, if anywhere, can we make this series converge to 1/x? So if it is convergent, we have a rule, the first term divided by the quantity 1 minus the ratio. We can use that formula to find the sum of the series as long as the common ratio is less than 1. So what we're going to do here is I'm going to take this common ratio and I'm going to say, okay, well, negative x minus 2 over 2 needs to be less than 1. Simplifying that, I can get rid of the negative, multiply by 2 on both sides. I have x minus 2 less than 1. When I multiply by 2, that becomes 2. So negative 2 less than x minus 2 less than 2, or that x is between 0 and 4. So this is my radius of convergence, or my interval of convergence here. I guess the radius would be 2. So as long as my x value is between 0 and 4, we can say that this Taylor series, this is going to converge for any x value that is in the interval from 0 to 4. And that sum, it's going to converge to the sum of the first term divided by 1 minus that constant ratio, negative x minus 2 over 2. And if we simplify that, we end up with 1/x. So it converges to 1/x for any x value between 0 and 4. And my Taylor series polynomial is what I have circled here in this box.